Hey guys, Ms. Gosling here. In this video, you're going to learn about gravity. By the end of the video, you'll be able to solve problems involving gravitational forces, fields, and potentials. So let's go ahead and get started, because that's a lot to cover. So first of all, I want to introduce you to the equation for gravitational force. Gravitational force is given using Newton's law of universal gravitation. And we are going to go ahead and define our gravitational force as being equal to a constant, big G. And in this case, guys, this constant, G, is 6.67 times 10 to the negative 11th times the masses of each object that are experiencing that force, divided by the distance between those objects squared. So, if I'm looking, for example, at the sun and the earth, my gravitational force between the sun and the earth is going to be equal to the my constant G, 6.67 times 10 to the negative 11th, times the mass of the sun, times the mass of Earth, divided by the distance between them squared. Now, I do want to note that when I look at R squared, you can see the sun and the Earth are not single point objects. So you may ask, where do I measure my my force from? Where do I measure my distance from? And that's going to be the distance between their centers of masses. So between the centers of my two objects. Just since they're both approximately spherical, we can assume the center of mass is the center of the Earth or the center of the sun. So let's go ahead and look at an example. Bertha has a mass of 50 kilograms, and Abdul has a mass of 75 kilograms. Abdul and Bertha stand 20 meters apart on the dance floor. They feel an attraction towards each other. What is the magnitude of the force of attraction? So we are given that Bertha has a mass. So MB, the mass of Bertha, is 50 kilograms. MA, the mass of Abdul, is 75 kilograms. And the distance between them, R, is 20 meters. We also know that G is equal to 6.67 times 10 to the negative 11th. I like to remember that big G is bigger than little g, if that helps. And we're trying to find the force of attraction between them. And given that we are in our gravity unit, gravity topic, and given that we are talking about the attraction between objects, we know that that force of attraction is going to be the force of gravity, which is given by the equation Fg. Let me catch my writing up to my speaking. Fg is equal to gmm over r squared, or in our case, Fg is equal to g times the mass of Bertha times the mass of Abdul over the distance between them squared. Now I'm ready to go ahead and sub and solve, and I will get that the force of gravity is equal to 6.67 times 10 to the negative 11th times 50 times 75 all over 20 squared. Calculating that out, I get that the force of gravity is equal to 6.3 times 10 to the negative 10th newtons. Now, I do want to mention here, guys, we're going to be dealing with a lot of scientific notation. Please be careful with how you put this in your calculator. It can be really easy to put scientific notation in the calculator incorrectly, and thereby get an incorrect answer. So just be really careful. Gratuitous use of parentheses is very helpful for these problems. Okay, so moving on, we've talked about what gravitational force is. I also want to talk about gravitational fields, and here is actually where we get little g. So you remember on Earth, we know that little g is 9.8 meters per second squared, and we define our gravitational field as our acceleration due to gravity at a given point in space. So that means that our gravitational field is equal to the gravitational force divided by whichever mass I'm not looking at the field for. So for example, if I'm looking at my Earth-Sun system, and I've calculated the gravitational force between them, but what I want is the gravitational field due to the sun, then I know that my gravitational force, my gravitational field, is equal to the force of gravity between the sun and the earth, and again I want little g for the sun, divided by the mass of the earth, since I really only care about what's going on at the sun. Now let's go ahead and expand this out. So we know that little g then is equal to the force of gravity, which is g times big G times the mass of the sun times the mass of the earth divided by the distance between them squared, all divided by the mass of the earth, or simplifying a little, G is equal to G times m over r squared times the mass of the earth. The masses of my earth and my sun are going to cancel out, and what I'll get is that the gravitational field of an object is equal to big G times that object's mass divided by the distance I am from the center of mass of the object squared. And again, I do want to just be very clear. We're looking at the distance from the object's center of mass. So if I'm on the surface of the sun, for example, I'm not at its center of mass, so I do still have a distance that I can look at. So let's go ahead and look at an example. The asteroid Ceres, I don't need to highlight that, I don't know why I did. The asteroid Ceres has a mass of 7 times 10 to the 20th kilograms and a radius of 500,000 meters. What is the gravitational field at the surface of Ceres? So we've got our asteroid Ceres, and we know that we are looking at this distance here, and we want to figure out what little g is. Now, I do want to mention, let's go ahead and just run through this problem, and then we'll talk a little bit about why we bother with gravitational fields. So we are given the information that the mass of Ceres is 7 times 10 to the 20th kilograms, that its radius is 500,000 meters, and that its gravitational field, and that big G is 6.67 times 10 to the negative 11th. Okay, so continuing forward, our unknown is little g for Ceres. So our gravitational field at the surface of Ceres. And I know that that is given by the equation G equals Gm over r squared, which means that I'm ready to go ahead and sub and solve. Now I know I need to use this equation because I don't know the gravitational force that an object is feeling on the surface of Ceres. What I know is the mass of Ceres and the distance I am from its center of mass. So little g here is going to be equal to 6.67 times 10 to the negative 11th times the mass of Ceres, which is 7 times 10 to the 20th, divided by the distance I am from its center of mass. So that's going to be the radius of the planet, which is 500,000 meters squared. And when I throw that in my calculator, what I'll get is that little g is 0.19 meters per second squared. So if I were to take a box and go to Ceres, that's the rate at which that object would fall. Okay, so I know this has been a lot of equations, but the last thing I want to talk about is the gravitational potential. So we've talked about gravitational potential energy, but I want to differentiate that from the gravitational potential because they are slightly different. So the gravitational potential energy tells me how much work it takes for me to lift an object up to a specific point. So potential energy is the amount of energy that something acquires because of its position in a gravitational field. The gravitational potential is the ability of the object to do work. So potential energy arises because of the difference in potential in different points. So for example, a box on Earth, or a box on the ground, and a box up on the air have different potential energies because there is a potential difference between the two. So we're going to define the gravitational potential, which we use Vg to represent, as G times the mass of an object, so 6.67 times 10 to the negative 11th, times the mass of whatever object I am moving away from. So for example, if I'm looking at the potential of an object at a point above the Earth, what I'm going to be looking at is I'm going to be using the mass of the Earth for that mass. And little r, which is going to be how high I am, how far away I am from the center of mass, or whatever my zero potential is. And I want to go ahead and just give one analogy here. We could kind of say that the force of gravity is to little g as potential gravitational potential energy is to my gravitational potential. So the gravitational potential is independent of whatever mass I'm putting in the field, and my gravitational potential energy, which is actually given by mass times my gravitational potential, is equal to is dependent on the specific mass that I put into it. So my gravitational potential I can use to solve problems involving a variety of masses, while my gravitational potential energy is specific to a given mass. So my gravitational force is equal to mass times little g on a given object, and my gravitational potential energy is given by mass times my gravitational potential. So you can kind of see those parallels between little g and between my gravitational field and my gravitational potential. So moving on, we can calculate. So we're going to look at one last example, and we're going to calculate the potential at the surface of Earth. The radius of the Earth is 6.4 megameters, and the mass of the Earth is 6 times 10 to the 24th kilograms. So what we can say then is that we are given the information that the mass of the Earth is 6 times 10 to the 24th kilograms. The radius of the Earth, which is the distance from our center of mass, which we're going to define as our zero potential, is 6.4 times 10 to the 6th meters. And that big G is equal to 6.67 times 10 to the negative 11th meters. Or not meters, excuse me, guys. So moving on, our unknown here is our gravitational potential, V sub G. And my goodness, I'm accidentally using the highlighter. Let's go ahead and fix that. My gravitational potential, Vg. So we're going to connect all of our givens and unknowns using the equation Vg is equal to negative Gm over R. And I do want to mention that negative sign arises because as I get closer to the center of mass of an object, I'm losing potential energy. So for example, my potential energy on Earth is lower than my gravitational potential energy if I'm standing on top of a desk to jump off of it. So that negative sign is representing the fact that it requires work to move farther away from the Earth, and you are doing work when you get closer to the Earth. So anywho, moving forward, we have our equation. Let's go ahead and finish and sub and solve. So we know that Vg is given by negative G, so negative 6.67 times 10 to the negative 11th, times the mass of the Earth, which is 6 times 10 to the 24th kilograms, divided by the radius of the Earth squared, so the distance I am from my center of mass. Sorry, not squared. The distance I am, just divided by the distance I am from my center of mass, which is 6.4 times 10 to the 6th meters. So plugging that into my calculator, and again, being very, very careful with my exponents. What I will get is that my gravitational potential is negative 6.3 times 10 to the 7th joules per kilogram. And just a heads up, joules per kilogram are going to be the units for my gravitational potential, which makes sense because when you multiply that by mass in kilograms, that gives us our potential energy in joules. So anywho, guys, here's how I solved this problem. So let's go ahead and quickly talk takeaways. So first of all, the gravitational force between two objects is given by F equals gm over r squared. And massive objects generate gravitational fields of strength G equals gm over r squared. We can also define the gravitational potential, Vg, as negative gm over r. And we can use it, and from that we can actually also say that our gravitational potential energy is negative gmm over r, right? Since we define our gravitational potential energy as mass times our gravitational potential. The last thing I really want you to take away from here, guys, are the relationships between these different concepts. So our gravitational force is equal to mass times g, and our gravitational potential energy is equal to mass times our gravitational potential. With that, you now know everything there is to know about gravity. It is your turn to try solving some problems. Best of luck and happy solving.